Hello, today we are in Titan microscope in STEM mode and I'm going to show you how to fight with STEM distortions. So let's tune a little bit, maybe correct astigmatism and optimize focus. When ready, we press acquire button. So scanning starts, but it's relatively slow, it takes time, and during that time anything can happen. Sample can be drifted, and as a result your final STEM image will be distorted. So how to fight with that? Let's go to STEM control panel, left upper corner, and there is a control of rotation. So let's press button 90 and click acquire again. Another acquisition starts, but now it's 90-degree rotated. The point is, the horizontal scanning direction is fast and vertical direction is slow. When we rotate 90 degrees efficiently, we exchange them. Now let's do same with digital micrograph. Right now it's continuous acquisition using DigiScan. Well, I'm shooting from hand, so it shakes a little bit. Let's press button record and acquisition starts. As I told you, the horizontal scanning is fast, thus I don't expect much distortions in that direction, but vertical scanning is slow. So when we move from top to down, a lot of things can change. Sample can drift. Thus, effectively, we end up at a position very different from what we started with, and that introduces distortions. Now let's go to DigiScan, field rotation angle, and input there 90. Don't forget press enter. Well, then press record button again, and another acquisition starts. Now 90-degree rotated. Well, our direction of fast scanning now is the direction what was before direction of slow scanning. Strongly distorted, but now it will be less distorted, and that would create some material for reconstruction. In summary, at the end, we will obtain a couple of images strongly distorted in mutually perpendicular direction. So there is a great hope that having them both, we can reconstruct the true image. We can do it differently. I already opened a special script which is called acquire unrotated or rotated images, and we can just run this script. So the acquisition starts. Right now it's acquisition of the original orientation. You see the capture original. Unfortunately, you cannot see live the images. It will be only shown after the acquisition finishes. But now it is, and the rotated image is acquired. Well, my camera, please focus. Yeah, here we are. I'm trying just to make both images the same size. Well, acquisition is finished and we have a couple of images, one in the original and another in the rotated orientation. Then let's move to offline. You know, microscope time is quite expensive. We cannot afford using it for YouTube fun, but for offline treatment we have a plenty of time. Let's open STEM Core 2 and treat previously recorded images. Record it like I showed you. 2 scans for each image. For instance, here is some image of a cubic particle recorded in the original and in the 90-degree rotated orientation. In the original orientation, it was a great drift towards left up, which caused some shear to the left and a little bit vertical contraction. After we rotated 90 degrees, the drift turned to right up. So correspondingly, we see some shear to the right and again some vertical contraction. Let's click first at the image of the original orientation and second at the rotated orientation. The sequence is important. Then press correct drift. The system evaluates the direction and the magnitude of the drift. And knowing that, corrects for the linear drift both images. As an output, you have the original orientation corrected and the rotated orientation corrected for the linear drift. So you might see that in both images, the shape of the cubic particle is restored quite reasonably. Okay, so let's then close all images. We can apply this procedure to atomic resolution images. For instance, here, perovskite lattice recorded in the original orientation and in the 90-degree rotated orientation. You might see that in the first case, we observe something like monoclining distortion due to the drift. And in the second case, the lattice looks like tetragonal lattice, although we know it's cubic. So we are going to correct that. Important, we should click correction on FFT and then click first original, second rotated image and correct drift. After some time you get the corrected images and you might appreciate that in both images the correct geometry of the lattice is restored quite reasonably. Okay, that was correction for linear drift. I should stress that the nonlinear correction is another story, maybe a little bit more complicated. We will cover this topic the next time. Thank you.